SwayamPrabha. Digital India. Educated India.
So, we claim, as I said before, that chi gamma for gamma in Zn form an orthonormal basis. Yeah, so again I am going a little bit quickly over this material. One reason is that we have spent a lot of time on QFT over Z2n, and another is that it is definitions, right. So, I would like us to spend more time in understanding algorithms and cryptography, how to build it and so on. So, this is still like its definitions. So, now who can prove this for me? So, what do I need to prove? To show that it is orthonormal, I mean I just look at the inner product between two of them represented as vectors, and I should show that if the two sort of subscripts are unequal, then this is 0, otherwise it is 1, right. And that will turn out to be very easy. So, again we will go over it a little bit quickly. So, this is the term I want to analyze. Alright. So, where were we? We were looking at the inner product of these two characters. Okay. So, we will just write this down. So, this is the expectation over x chi sigma x conjugate chi gamma x. Remember that this is just by the definition, because I am looking at them as two vectors, right. So, basically I will take the inner product of these two vectors, this will range over all x, right. So, I will get exactly the summation, and instead of writing the summation I am looking at the expected value. Anyway, the probability will be the same for x is uniform, right. Okay. So, now we will use our findings on conjugates of characters. So, this will be minus sigma x, right, chi of minus sigma x chi gamma x, okay, which in turn we said is chi gamma minus sigma x, okay. And now we know from the properties we proved, right, that if this is equal to 0, then I get 1, right. So, the question is whether gamma minus sigma is 0 or not. So, it is 1 if gamma minus sigma is 0 and it is 0 otherwise. So, this follows from the properties that we have proved so far. Is it clear? Yeah? Okay, great. So, what do we need to do now? We need to figure out what are the coefficients. Okay, so we have our, we have our standard basis anyway, and now we worked out what is our new basis, our Fourier basis. So, that is these characters. So, now the last thing that we need to do before we understand this change of basis is just to figure out what are the coefficients. And the coefficients, to figure that out, we will use this idea that we just saw, right. So, basically I want to work out what is g hat of gamma, right, and what we saw is that this can be written as what? The inner product of chi gamma and g, right. So, this is expectation over x, right, chi gamma of x conjugate g of x. Okay, and this is also analogous to what we had in Z2n. So, now let us similar to Z2n, let us just write down what is the Fourier transform. Okay, so it is what we said. So, when we go from the standard basis to this Fourier basis, we want I mean we want to, the map is called the Fourier transform. Now recall that it is not obvious that this Fourier transform can be implemented efficiently. So this is something we have to still show. So remember that in the case of Z to N, we showed that the Fourier transform could be implemented using the Hadamard, right. Now the Fourier transform is different. So even though algebraically a lot of the properties are very naturally, they follow from what we saw before, it is not at all the case that the circuit that we had before is going to compute this, right. So we still need to worry about that, but let us go there. So first of all, we will just define what the Fourier transform is. So the unitary transformation that takes a function to its Fourier representation is the Fourier transform. Okay, so 1 over square root n summation over x g x x goes to summation over gamma g hat gamma gamma. Alright, good. So once again we will take a couple of special cases as examples. So let us look at this example. This is again analogous to what we just saw for Z to N. So if g x y is defined as square root n when y is equal to x and 0 otherwise, right, then the vector representation of gx is x, and g hat x gamma is expectation over y chi gamma star y g x y, which is chi gamma x star, right. This is because gx of y is only non-zero when y is equal to x. Okay, so basically x can be represented using the change of basis as this. Okay, so this is our Fourier coefficients. So note that in all that we have seen so far, we did not use any special structure of capital N. Okay, so oftentimes we will think of capital N as 2 to the small n, like we will think of it as a power of 2, but it need not, I mean what we have seen so far does not use that. I just wanted to point that out. Anyway, we will see when we need it to be a power of 2 or not. Yeah, coming back to what we are doing and why we are doing it. The point is that in the classical setting, this Fourier transform would take exponential time to compute. Here we can compute it in polynomial time, and moreover we can show that measurements let us get something out of it. Okay, so in all the algorithms that we see, finally obviously you have to measure to access the information in the system, and the places where we get speed ups are where, you know, we can apply this QFT, get some interesting information that is amenable to measurement. Okay. So, circling back to your question, there is something extremely specific about the transform that we are doing. There is a special Fourier basis, right, and it is only for that transformation from the standard basis to this special Fourier basis that we are developing the theory on, you know, how to implement it efficiently, and when you run it, then what do you get, what are the coefficients, you will measure it with some probability, what do you get. So, it's very, very far from just a change of basis, right. It is just a change of basis, but it is a very, very special basis, and being able to implement it efficiently. I know I am repeating myself, but this is I am repeating myself because you know, and I will keep doing it, because this has to really, everybody has to get this, because this is the main thing. Okay. Very good questions. Any other questions?